going to do quadratics. Actually, the technical correct name would be quadratic functions, because they are functions. They will pass the vertical line test. And so probably the number one thing you need to know about quadratics is what they look like and what makes something. So far, all you've ever done was lines. Everything's been linear, 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 linear. What makes something quadratic? The weird part is, do you all hear the word quad in quadratic? Everybody thinks it's going to have something to do with 4 because they hear the word quad. That's not the case. Functions that have to do with force powers are what we call quartic functions, not quadratic. So you tell me what makes this one different from all the ones you've just done. What's different in that one that you did not have in any of your systems of equations, your linear equations? Oh, yeah, help yourself, I got it. Do you need the hot glue gun or just the glue? Okay, it'll be... Okay, there's more than check size. There's one for little guns and there's one for big guns. Come back now, because I have big gun ones too. Okay, so sorry, video people. There was a brief pause there. Should have paused it. Oops. So anybody figure out what's different there? There's not something screaming at you that you didn't have? The power. We didn't have any exponents. Yeah, but, okay, you had the bx plus b. That's mx plus b, just different letters. That's a number times x plus a number. That last two parts, that is a line. The only thing different is I added another term, and now you have a square in it. And everything changes once you start putting powers on things. The graph goes totally different. You will not draw lines again. Everything else, everything from here on out is curves. If you start putting powers on your variables, you get curves. So this is going to not be a line, and it is going to be quadratic. So to be quadratic, by the way, this is what we call standard form. To be quadratic, it must have a squared term, has to have x squared in it, and that has to be the highest power. If it was x cubed or x to the fifth, it would not be quadratic. To be a quadratic, it has to be x squared, and that has to be the highest power in it. Now, I could use Michaela as my witness. What? Will they see quadratics ever again?
Yes. I don't know.
How do you solve the bottom of every problem? Yeah, you do them a lot.
You have the big fat ones?
There, look in the other sack, because that sack may be the little ones and the big ones may be the others. Okay, so what our goal today is learn how you graph these puppies and how do they look different. So I'm going to get you to do the very first one by hand here. We're going to do the simplest quadratic there is. To be a quadratic equation, there has to be x squared in it. You do not have to have the other terms. You don't have to have the bx and the c. You can, but not required. So to do a quadratic, as long as there's something squared, you're going to get it. So we're going to graph the simplest quadratic there is, plain old ordinary x squared. And y'all have to see the pattern with the numbers to understand why we get what we get. So we're going to do the little old-fashioned t-table here, and it'll probably 1, 2, 3 ought to be sufficient. So what's going to happen when I put 0 in for x and square it? It's going to be 0. And 1 squared is 1, and 2 squared, and 3 squared is 9. Okay. Now, I also want to ask you, though, does it change if I did -1, -2, and -3? Because when I put those in and square it, it's still going to be positive. So I'm going to get 1, 4, 9 again. So when you go to plot this, you're going to have 0, 0, 1, 1, but you also have -1, 1. So you're actually going to get what we call mirror points. You're going to have the exact same point on both sides of the origin. The next one's 2, 4, and we also have -2, 4. You're going to go 2 up, 2 over, and 4 up on both sides. And then you're going to have 3 over and 9 up on both sides. Okay. What's it look like? Okay, anybody you agree? Is it kind of a U? A V-ish U. I like that. Okay. But yeah, we call it a U-shaped curve. Sometimes it can be, we're going to discover here, sometimes it's wider, sometimes it's more narrow. But in general, yes, it's called a U-shaped curve. Anybody know the official mathematical name of it? Yes. Get these bonus points of the day. It is indeed, oops, that didn't change, known as a parabola. So, please say parabola, not parabola. Okay? Parabola. So, it is one of the most well-known graphs in all of mathematics, by far. There are some key points we need to know on our parabola that we identify all the time. What would you guess is probably the number one most important point on that curve? And you called it the right thing. Yeah. That base of the curve, that's called the vertex. We are going to spend a lot of time worrying about where that vertex is. Why would you care? Particularly when we turn these into real-world problems, and you're going to see real-world problems on just about every single day of this section, because these have tons of applications in the real world. But isn't that the minimum point on the curve? So since that's the minimum point, anytime out in the real world you come up with an equation, that's the equation of a quadratic, and you need to minimize it, you want to find out what the minimum value will be, you just have to find the vertex. And in a little bit, we're going to turn them upside down so the curve's on top. Then the vertex is the maximum value. We'll be doing some problems later where we want to maximize our income. The maximum income is going to happen wherever the vertex is, if it's an upside-down parabola. So finding the vertex is going to be really key for lots of reasons. That's going to be the major thing we're going to look for. Okay, a couple other things that we name within a parabola. If you drew a line smack down the center of it, what does that do to it? Divides it in half. What do you call it? What's the name for something when it's exactly the same on either side of something? What did you say? Identical? There's a mathematical kind of geometry term. Starts with an S. Symmetry. There we go. It's symmetric. It's balanced on either side. It's got symmetry. We call that line I drew down the middle the line of symmetry. So you're going to be asked to find the line of symmetry. But it helps if you don't try to write with a line. Okay. So that's the line of symmetry that runs down the middle. And we'll come up with how to find this equation here shortly. One thing I want to note, what kind of a line is it? It's straight, but when it's straight up and down, it's a vertical line. How did you write the equation of vertical line? X equals. So I'll be asking you to come up with the equation of the line of symmetry. So it's always going to be X equals whatever the X coordinate of the vertex is. It has to go through the vertex. So whatever the x-coordinate of the vertex is, that's how you're going to get your line of symmetry. If the vertex is over at 2, then it's going to be x equals 2. So whatever x-coordinate you're going through, that's the number you put in there. All right. So the question is, how do we start changing that? That was the graph of good old basic x squared. What if I want to start changing that equation? What if I want that parabola to move? Up, down, left, right, get wider. Yeah. You remember actually I've got some of them written up here, over here on the whiteboard. Remember doing absolute values? We had the greatest integer of the stair steps, and you had to shift them. So if I put a +3 on the end of it outside the absolute value, what did that do to every graph? +3 on the outside. She's saying left 3, you all agree? Because there's a difference on whether I put it outside the absolute value or I put it inside the absolute value, like this x minus 5 that's inside the absolute value. Anybody want to agree? I got one answer. I got it right 3. I got it up. Okay. Well, you guys have obviously forgotten. So you're going to do this every single graph we ever draw, which shows another 4 or 5 times. These rules are going to happen, same rules every single time. At the moment, I have plain old x squared already on there. I want to try to alter it, so I'm going to hit tab, and I'm going to put in x squared. We'll put the +3 on it. If I put +3 on it, which way did it go? It went up 3 units. When you add it outside the function, it goes up 3. So if I put -5 on the end of it, it would go where? Down 5. The number on the end always makes it go up or down. Now, how did I make it go sideways then? If it was inside, but what's inside? Over there on absolute value, it was inside the absolute value. And here you're inside what? Yeah. You have to be inside the square because it's the square that's making this be a parabola. So if you want to make it go sideways, I'm going to go back up here and alter this one. I want to be inside the square. You have to do a quantity and do x plus 4. Now, where would I have to put the square? It'd have to be on the outside of the parentheses. And by the way, you have an x squared key. If you want to square something, you just hit that. You don't have to mess with the caret. It just automatically puts the square on something, which is faster. Okay. So now, which way is it going to go if I put a +4 on it? I got to vote for left 4. Anybody want to fight? Argue? We got left 4s? Yep, we went left 4. So when you replace it, you're going to, actually the more you start to see this, every time it's inside a quantity, you're going to go opposite direction of whatever the sign is. So if it's inside some quantity, think, oh, I should go opposite. If it's outside the quantity, it's going to keep the same sign. Inside is always shifting you left and right. Outside is always shifting you up and down every single time. So I'm going to alter one here, and we'll see how good predictors you all are. I'm going to make this become, not quite that far, I want it to be x minus 6, and on the outside I'm putting a minus 3. Votes for right 6, down 3. Anybody else, y'all buy that? Well, I want to add one more thing. What if I throw, out in front of it all, I pop a negative on it? Okay, vote for goes downward. Changes the width. Anybody else? I think you're just going to go down, okay? So I did go right 6. If that was minus 6, I went right 6, down 3, And because of the negative out front, that always, it used to change the slope, but now we're not doing lines, so it's technically not a slope anymore, we're doing curves. But it actually, what we say is it flips over the x-axis. It's a reflection. So anytime you see a negative out front, it's going to flip over the x-axis. So what's left to change? I'm going to go back to basic again, and you kind of really have to see these. I want to throw a number in front of it. And I'm actually going to throw it in front of just a plain old ordinary x squared here. Okay, what do you think is going to happen because I threw a 3 on it? First to Logan. What's it going to change? A vote for whiter. Yeah, whiter? Okay. Why? I would have thought so too. Yes. Nick said it's like a steeper slope. Technically, once again, it's not a slope, but yes, it's making all your y coordinates larger. So all your y coordinates are going up fast, so it actually makes it get more narrow. So if I throw a 3 in front, I'm going to get a narrow, skinny little parabola. So what would I have to put in front to get a wide parabola? Okay, Nick says 0.1. What do y'all think about that? Okay, let's try it. Go back. Yeah. Putting a fractional value on it, something between 0 and 1, a fraction between 0 and 1, will make it get much, much, much wider. And in that case, where we put a 1/10 on it, that really made it wide. Now the question is going to be, how do you guys make that happen when you're graphing by hand? How do you do the wide and the narrow? What makes that happen? So we're actually going to go try that a second. I'm going to go back to, where am I on time here? Ooh, good place to stop.